Hello guys, you're in for a treat today. This is a PCB obviously, but it's an ESC. It's an electronic speed controller used in electric bikes and electric scooters. Basically all electric vehicles, even robots use these kind of PCBs. As you can see, we have some MOSFETs here. It's about 6 per phase. These are phase. You can see they're written A, B, and then there's a C. So I had previously removed all the wires from the PCB. Where are they? Where did I put them? There they are. So I previously removed these 3 wires from the PCB. These were used for taking power from the controller and giving it to the motor. Those are for the phases. So what I want to do next, now that I've removed some components, is I'm going to start removing some of these, all these MOSFETs. They have to go, because what I want to do is to clear out enough space so I can do proper analysis how this entire circuit works. Currently studying how electric vehicles work, how electric controllers work. These are basically the most complex parts of the entire system. If you can figure out how electronic speed controllers work, you can then be free to build electric vehicles. So I'm going to start my analysis with this board. I've had this for like 4 years, and this was actually one of the very first board that I spent money on buying back in 2019. It's about almost 5 years now, and unfortunately it didn't last a month with me because I did something terrible and it broke. So I had to wait another several months to gather some money to buy a new board and a new ESC, and that ESC is still on my e-bike till this very day, and it still works after 4 years of usage. So this ESC could have lasted a lot longer. It's actually both of ESCs are very similar. This one, the only difference is it uses 100 volt capacitors, while the other one uses 80 volt capacitors. While also these MOSFETs, they're rated up to 100 volts or 80, like almost 90, almost 100 volts, whereas the other ones, they can barely go up to 80, and that's because this controller was rated for 72 volts, 84 volts maximum battery voltage, whereas the other one was rated for 60 something volts battery voltage. So this controller in my eyes is actually better because it was built for 3 kilowatts, actually more than that, but let's just 3,600 kilowatts, maybe 50 amps and 72 volts. That you can do the math. So yeah, so like I said, I need to do some reverse engineering. I know that the MCU right there is responsible for like everything, and there's some programming that needs to be done. I don't know if I can do like firmware extraction or if I can find the firmware online, but be that as it may, first step I'm gonna do is just like clear out this board so I can see everything properly. So removing the caps, removing the this entire big giant block of aluminium. It's just a heat sink, and then removing all these MOSFETs so that I can get a better view of what is going on, and then I will be able to wire it up in a CAD software like KiCad or EasyEDA. So that's the plan. So I'm just gonna place my camera here, see if I can get a good view. So I'm gonna start with this MOSFET here, and hopefully let's see if it goes. Let's see how it goes. So I've got my soldering iron here, and see if I can get a better view. Right. And I'm gonna start heating up the legs. Oh, first things first, I doubt that I'll be able to like melt all of them one after the other. So what I'm gonna do is I see that this is bolted here, right? So it's bolted. I'm gonna unbolt it. So let me grab myself a screwdriver. See if it comes out. Oh my gosh, my aim. There we go. It's actually not too bad. It's not bad at all. It's held on by a bolt and some sort of nylon material, and it presses this MOSFET onto the aluminium backplate, which just serves as a heatsink. Then, as you can see, there's a lot of like mounting holes at the bottom here. These ones up here are for the MOSFET, while the ones at the bottom here are for mounting this entire PCB into a case. Most of the time it's an aluminium case because, well, aluminium is a great heat conductor, but at the same time you don't want aluminium touching this guy. So what they do is they separate the actual MOSFETs with something called Kapton tape. See that? Can you see that? So they separate it with Kapton tape as well as a little bit of thermal paste. This Kapton tape, the only job is just as an insulator. It allows heat transfer between the MOSFET and the aluminium block, but it prevents any shorting, because as you can see, all these MOSFETs, they're all attached to the aluminium plate, but you don't want them all shorted to each other, because as you know, this big heatsink, this part of the MOSFET which has a big plate is a current conductor, right? It's a part of the circuit, so you don't want it shorting out with the rest of the other MOSFETs, so that's why you need to isolate it. You wouldn't need to do this if each of them had their individual heatsink, but then again, that's not good for mass production. So yeah, this is actually pretty good. So I've got this bent out of the way. Now I just need to solder it off of the block. See how that goes. I'm just gonna apply some heat, wait for a few seconds, let the heat soak into the components. Let's see if that's moving. Yeah, it's moving. Okay. Let me try this technique. I've seen it work several times. I'm just gonna apply a bunch of soda all across all the legs, and while I do that, hopefully when I heat up the big giant blob of soda, it would allow all the legs drop out at the same time, so it will make it easier to work with. So see how that goes. Hopefully this isn't, I hope I don't regret this. Seems to be working. I'm gonna pull from the other side and see. Doesn't seem to be moving yet. So, it's not easy at all. Okay, seems to be moving. Yeah, the legs are moving. Oh, there we go. We got some rock. Okay, that's a good sign. It's rocking, so let me use my finger to pull. Okay, it's moving. Oh, it's hot. That is very, very hot. I need to keep this thing there long enough. It's a bit, this is a bit chaotic, isn't it? Try from this angle. See if I can show you guys what I'm doing. Okay. Yeah, keep coming. Yeah. Oof, damn it. I think I need some gloves. But it's coming. The heat is transferred all the way from the legs to the very top here, which is very surprising. I think I need tweezers or something. Let me just do this. Let me get some tweezers. I keep burning my fingers. go. I got some tweezers. Hopefully this would help. You know, pull it out. Pull it out. Oh gosh. I'll just position my tweezer right there, and while let me see, put it like this, and then while I heat it up, I would yank it in that direction, and hopefully it would break free. So let's see, one more time. All the solder is already melted. This is difficult, I'm not gonna lie, guys. It's really, really difficult. Okay. Yeah. Yes, good. How are you? Hi. Sorry, I'm in the middle of something, but.
John.
You speak English?
I speak English only.
Yes, English only. Sorry.
Okay.
Yeah.
I want someone here.
What?
I want someone here. I'm going to meet with him, but I'm still waiting for him.
Who are you waiting for?
Someone who is the guide.
The guide?
Yeah.
What do you mean by guide? There we go.
You don't understand the guide. The guide.
Guide.
Yes.
Guard or guide? Is it like a security?
Yes, a security.
Security, yeah?
Security guard.
Okay. You can go out. I think there's a security guard outside. Did you see him?
No. Someone who is the older one.
Okay.
You know him?
No, I don't know him.
Okay.
Alright, thank you.
So, thank you.
Yeah. Okay, so we successfully removed the MOSFET. It still feels pretty hot. I'm quite amazed by how quickly the heat transfers from the legs to this plate here. It was really hot. I think my fingers are burnt. I think my fingers are burnt. But yeah, that was painful. I think there has to be an easier way. I need to figure out some other way to take these things off without hurting myself. But there you go, guys. We have one MOSFET removed. We have 17 more to go. It's a lot of work. Anyways, thanks for watching. Goodbye.